Hello, in this video I am going to talk about Fisher projections. Now Fisher projections is another way of drawing molecules in 3D format by using horizontal lines and vertical lines. An example is this of D-glyceraldehyde. In this structure we have the stereocenter, which is the carbon here, and the horizontal lines, I want you to visualize them as if they're coming out of the screen. In other words, projecting towards you. And then I want you to visualize the vertical lines as if they are behind the screen. So they're going away from you behind the screen. Now when we do that, at every stereocenter, we need to visualize the structure in that format. So for threos, we can draw the structure in that format. Ribose and even glucose, we can draw the structure in that format. Now, once we draw the structure in that format, we can determine the configuration for each stereocenter. So let us do the configuration, say, for threos. So let us label this as carbon number 1, carbon number 2, carbon number 3, and carbon number 4. To determine whether we have an R or S configuration, we need to visualize these bonds clearly. So at each stereocenter, we need to look at the bonds that are horizontal as if they're coming out of the screen towards our direction. So once we do that, we need to look at the priority of the atoms connected to the central one. So here we have oxygen is going to be of priority number 1. And then we have carbon here. And we have another carbon that is carbon number 3. So between carbon number 3 and carbon number 1, we need to determine which one is of the second priority. The carbon number 3 is connected to an oxygen, which is connected to hydrogen. Carbon number 1 is connected to an oxygen, but there are two bonds. So there's a sigma bond connection and a pi bond connection. So we count that as two connections. So carbon number 1 is connected to two oxygen atoms. So it's going to be of the second priority. So priority number 2. Then priority number 3 is the one over here. So that means we are going clockwise. So the stereochemistry at this position, if we are going clockwise, remember clockwise, we say this R. Counterclockwise, we said is supposed to be S configuration. But there's a catch. You need to make sure that the fourth priority, which is the lowest, must be behind the screen. In this case, this priority is actually coming out of the screen towards where we are. So then if the configuration was R, then we need to give it an S. So therefore, this is going to be S configuration. Okay? The next one, we can also do the same. If we do the next one, you'll realize the next one is going to be an R configuration for carbon number 3. So here, there are only two stereocenters. So that means we can only determine the stereocenters for those two. Let us try to do another one. Let us find the configuration for this one here. So this is priority number 1. Then this carbon is connected to two other oxygen atoms. This carbon is connected to an oxygen and another carbon. So this is priority number 2. Then priority number 3 is this one here, that is carbon number 3, so which means we are going counterclockwise. So counterclockwise is supposed to be an S configuration, but this hydrogen of the 4th priority is supposed to be facing away. Because it is horizontal, it means it is facing up. We want it to be down, so we change that configuration to be R. So this is going to have an R configuration. Okay? Another way by which you can determine that, anytime you have an aldose, that is sugars that contain aldehydes, then if the OH is on the right, it's going to be an R configuration, R, R. This is going to be an R configuration, this is going to be an S, this is going to be an R, this is going to be an R. Okay? The best way is to practice and make sure you're able to get it right. Draw the 4 Fisher projections of aldotetraos and determine the relationship existing between any two of the structures. So aldo means we are using aldehydes. Tetro, that is from tetra, for 4 carbon atoms. An aldehyde that has 4 carbon atoms, and it's going to be a sugar. So the first one we can draw, we have carbon number 1, 2, 3, and 4, which is erythros. We already determined the stereochemistry for that. We can draw another one, so we can draw all the 4. What we are doing is just playing around with the stereochemistry to make sure we get 4 different compounds. So here there are 2 stereocenters, so 2 to the power of 2 gives us 4 stereoisomers that we can draw. Now, determine the relationship existing between any 2 of these structures. Let us count this to be A, B, C, and D. If we look at structure A and B, there is a mirror image, which means these are going to be enantiomers. If we look at the structure D and L, again we see a mirror image, so these are also going to be enantiomers. However, if we take any of the structures, for example, if we take B and C, those are going to be, let us figure out what it's going to be. We know that they cannot be enantiomers, so they could be diastereomers, and we could also think of mesocompounds. That is, if we can find an internal plane of symmetry. Now, in this case, we have S and S, then S and R. So that means these molecules are not going to be superimposable mirror images. Anytime we do not have a superimposable mirror image, then it means we can either have an enantiomer or a diastereomer. So these are going to be diastereomers because there's no mirror image between those two. So for B and C, they are going to be diastereomers.